Okay, so first I, of course, would like to thank the organizer for giving me the chance to present my work and to invite me in such a nice conference in such a nice place, and also thanks for the nice weather. So my name is Jean-Baptiste. I'm a postdoc in the Max Planck Institute for Extraterrestrial Physics in Garching, close to Munich. And today I'm going to talk about NOEMA 3D, which is the large program where we studied inflowing gas at subgalactic scales in massive star-forming galaxies at redshift 1 to 2. So a couple of days we had a very nice introduction by Linda Tacconi about some of the things in the field, but given that it is a very diverse conference, I thought it was important to go back to some of the main aspects and to kind of introduce a little bit the field. We'll be talking, of course, a lot about kinematics in this talk. And the first thing that I want to do is to talk a bit about cosmic noon and why this specific epoch in time is specifically relevant for galaxy evolution. And the first thing is that, of course, this region, so essentially between redshift 1 to 3, is a moment where the star formation rate is peaking. So at that time, galaxies were forming a lot more stars than there are today. And secondly, which might be even more relevant for the topic at hand, is that it's also the peak of molecular gas mass. So you can see here, and in generally, it's the peak of cold gas. And so that means that the galaxies at this epoch had gas fractions that were much higher than the one that we can see today. Now, moving away from that, one result that I want to highlight here was this study from KMOS 3D, which was made by Natascha Forscher-Schreiber and others, where when looking at a large sample of galaxies at cosmic noon, so between redshift 1 to 3, what they could see is that a lot of these galaxies, roughly 70%, had this typical, so these are the kinematic fields of these galaxies, and you can see that they have this typical red to blue pattern, which indicate ordered rotation. And now, in conjunction to that, and this is work that was led by Lilian Ni, who's a postdoc in our group, these galaxies, on top of being rotating disk, also have typically very high dispersion rate. And this is what you can see here. The dispersion, as you go to higher and higher redshift, tend to be much higher than they are in present galaxies. So kind of to summarize, the massive main sequence star-forming galaxies at cosmic noon are typically gas-rich, as we've shown. They are quite turbulent, given the high dispersion rate, and they can also be clumpy, as we've seen already in a couple of talks in the week. Now, another result that I want to highlight is this study, which was led by Juan Manuel Espero Salcedo, who's the postdoc in our group, in which we worked on a very large sample of galaxies observed with James Webb. So 1,500 galaxies overall at redshift 1 and 2. And this time we did a purely morphological analysis of these galaxies, so essentially by eye, going to galaxies and trying to classify what they would look like. And what we've seen is that roughly 80% of these galaxies have disk morphology, but on top of it, something which was quite clear is that a large fraction of these disks also have a spiral structure, and also some of them have bars, though bars are quite tricky to distinguish at this redshift. But typically we see a lot of non-axisymmetric features, and the question that one might ask is, what is the role of these features in the galaxy evolution at that redshift? So in the rest of the talk, I essentially want to try to answer these two questions. The first is, how is gas transported within galaxies at cosmic noon, given the large gas fraction? And the second is, what is the role of bars and spiral in the buildup of galaxies? So first, I want to introduce this work that we did back in 2023, which was led by Reinhard Genzel, in which we studied a sample of 9 galaxies with either H alpha or CO at redshift between 1 and 2.5. And there were so large massive galaxies on the main sequence. And I'm not going to go through all of them, but I want to highlight this first, the main target of the analysis, which is this galaxy called BX610, which was at redshift 2.2. You can see it here. And mostly what I want to show here is, of course, the results, but also a little bit the method, because this is what I will show then later on the NOEMA 3D survey. So the first thing that we do is we make this nice velocity map of the galaxy. So this is from CO. You can see the red to blue pattern, which indicates the rotation of the galaxy. And then what we do is we make a model, like purely a rotating disk model of this galaxy using the kinematic tool d_pi. And then we subtract the model and we look at the velocity residuals. Now the question is, how can we interpret this? We see that there is a nice blue blob here, a red blob on the other side of the PA, so that's essentially the axis of rotation of the galaxy. And so in order to interpret this residual, we need to try to see how the galaxy is in space, and this is a little cartoon to help you understand that. So essentially this is the near side and this is the far side. So this red blob here is going away from us and then toward the center, and the opposite on the other side. So this blue blob is going towards us and hence towards the center. So the interpretation was that these residuals are actually showing us radial inflows. And the thing which was quite surprising to see that these inflows, once you take into account the inclination of the galaxies, are actually quite large, of order 90 km per second, which is much bigger than what can be seen in the local universe. So now that was essentially the main result of this paper. And the question that we try to answer is, how can we go further than that? How can we do more? And that's when we turn toward the NOEMA instrument. So the NOEMA instrument, for those who don't know, is an array of 12 antennas, 15 meters in diameter, which is located in the Plateau des Bures in France, close to Grenoble, and which observes in the millimeter regime, so 0.8 to 3 millimeters essentially. And we developed this large program called NOEMA 3D, which is 1,100 hours of GTO. Not all the hours have been allocated yet, but we already have a large fraction of it. The targets are a massive main sequence disk again, quite large, and the important part is we go for very deep observation, 20 to 70 hours on source, on either CO423 or CO322, and mostly at a quite high resolution, or very high resolution, so of order 0.2 to 0.5 arcsecond. Now, the sample that we have so far consists of 10 galaxies at redshift 1 to 2. As you can see here, so these are JWST or HSC cutouts of the RGB images of these galaxies. You can see that they all, or most of them aside from this one, present very nice spiral patterns, maybe not so easy to see on the screen, but I mean you can see the spiral arms, and also quite a few, or some of them at least, have a bar. Now, what we did is essentially the same thing as what was done in the GAN-SOL 23 paper. The first thing that we do is to take all of these galaxies and we make the velocity maps, and you can see this typical red to blue pattern indicating nice rotation. The contours here are from one given filter from either the HST or JWST. And you can see that we see this rotation very well. And then in the same manner that we did before, we make a model out of this, and then we look for the residuals that you can see there. Now, I'm not going to go through all of them individually, but I'm going to focus on this one in the middle, which is one of the nicest case, which is called G43865. It's so a nice parallel galaxy, as you can see here, at redshift 1.12, also has a clump here. And when you look at the residuals that you can see in this panel here, what we see is this very clear blue residual on one side, and then though slightly lower amplitude, but red residual on the other side. And so if you take into account the orientation of the galaxy, which I made a little cartoon of here, what happens is essentially the same idea that I had shown before, which is that these galaxies show nice inflow, but this time, compared to before, what we can really tell is that these flows are following the spiral arm, and this is what you can see here and there. Just for completion, I'll also take another example. This is another galaxy, redshift 1.19. So same idea. We have the velocity map, we subtract the model, and now we look at the residual velocity. And you can see this nice red pattern here, which follows the arm essentially. Similarly, red pattern there, which follows the arm, and then some blue things here, and all of these correspond to inflow. So just to show that in many of these galaxies, we see, the two examples I showed mostly show inflow, but we have actually a mix of inflow and outflow, but these patterns always seem to follow the spiral arms, or in some other case, the bars of the galaxy. And the thing which is also quite important is that all of these flows that we see, or residuals that we see, tend to have very large velocity. And this is an update from a plot that we show in the Gensel 23 paper. And you see here the radial velocities that we infer for the flows, which are typically of order 50 to even 100 km per second. And there seems to be an increased redshift, which might correspond to the fact that galaxies at redshift 2 or so typically have larger gas fractions. Now I just want to show this very briefly, but also I was trying to compute for the galaxies in the Noema 3D sample the net flow rate, so essentially the amount of mass that you are transporting with these flows, and it seemed that there is a mix between inflowing and outflowing, but they seem to be of order of the star formation rate, a few times the star formation rate. So now to go briefly to my conclusion or summary. So Noema 3D allows us to study the kinematics of galaxies at redshift 1 to 2 with very high resolution and very high accuracy. Allows us to distinguish inflowing or outflowing gas, typically along the spiral arms and bars. The flows that we see have very, very large velocities of order 50 to 100 km per second. And we believe that this might be, funneling the gas toward the center and fueling star formation and whatnot. And finally, just pointing out that the survey paper, which is the one I presented now, will be probably appearing very soon on arXiv, and also we have a suite of paper that's from the Noema 3D survey, which also will be arriving pretty soon. Thank you.